guys, welcome back to my channel. If you're new here, make sure you take a second to hit that like and subscribe button for more fun physics content. We're doing a series right now called Abby Does Illegal Math, in which I try to get through the entire day without messing up unit conversions or order of operations. Let's see how far I get. Today, we will be returning to the tape experiment I did a couple weeks ago. In that experiment, we investigated electric force and interactions between charged particles. When objects come into contact with one another, this can be anything from rubbing to touching to even separating, electrons can be transferred between those two objects, creating one object with a net positive charge and one object with a net negative charge. By pulling pieces of tape off my desk, I caused that tape to become positively charged. I got two pieces of charged tape and attached one horizontally between two water bottles and put the second piece of charged tape under it, measuring the displacement of the top tape as the like charges repel each other. I tracked how much the tape moved, which was 3 centimeters, and used that to calculate the charge of the tape. I started out by making a free body diagram of the forces applied. These were the force of gravity in the negative y direction and the electric force in the positive y direction. Since the tape was unmoving, the system is in equilibrium, and thus the momentum of the system is 0, and the net force applied is 0. This means the force of gravity should equal the electric force. The force of gravity is calculated as the mass of the object, in this case 0.16 grams, times the acceleration of gravity, or 9.81 meters per second squared. This gives a force of gravity of 1.57 newtons. I set the force of gravity equal to the electric force. Notice here that the final equation looks a little funky. This is because we assume the charge of both tapes are exactly the same, since they are the same material and charged in the exact same fashion. Due to this, we can simplify the equation down after plugging in the values 0.03 meters for d and 9 times 10 to the 9th for 1 over 4 pi epsilon naught. I got a value of 3.98 times 10 to the negative 7th coulombs. This week, we're doing a very similar experiment, except this time we're treating the tapes as line charges instead of point charges. The math to calculate the electric field at this point will be quite different than it was last time. Instead of calculating the electric field at a single point, you calculate the electric field as if there were an infinitesimal number of points. This can be done by integrating the point charge equation. For this lab, instead of making those calculations, I made a model in Python that would approximate the electric field of the line of charges by iterating over a very small distance and adding all those electric fields together. I then used that information to calculate the net electric force on the top tape and the corresponding force of gravity. Let's take a look at my code for a minute. I started off by putting in my constants and values I determined in my last lab. Next, I inputted my equation for a point charge electric field, which I used during my iterations. I created a visual representation of the charges and my pieces of tape to better see the relationship between the charges and the electric fields. Next, I created initial values for my iterations and set some visual scales for the arrows I made to accompany them. I followed that up by coding the loops that iterate repeatedly throughout my function and calculate the net electric force. Finally, I created arrows to represent the net electric force and the net gravitational force. When I ran my model, this was the result. You can see the green arrows representing the electric fields at each point, and the yellow and white arrows representing the net electric force and the gravitational force respectively. Notice that though the green arrows point in both x and y directions, the net electric force is only in the positive y direction. This is because the x components of the electric field and thus the electric force cancel out. You can see the net electric force and gravitational force magnitudes calculated here. Comparing the net electric force in this lab versus my lab a couple weeks ago, the net electric force was actually larger in this lab. The discrepancies of these values come from the differences between treating the tape as a point charge versus a line of charges. The line charge model will end up being more accurate than the point charge model because it's more representative of the actual object being tested. That being said, there's still some error in the line charge method that can't necessarily be accounted for in my experiment. In this experiment, we negated air resistance, setting it to 0, and we also assumed that the charge would be uniformly spread out throughout the entire tape. Still, the results of the experiment seem valid and representative of what actually occurred in the experiment. Well, that's all I have today, folks. Hope you enjoyed this video and come back for more fun physics content.